pretty much what we will do this week is to continue with the same kind of test. Nothing basically changes except of the way that we calculate things. And instead of having two populations to compare the differences, we have more than two. So that's the subject this week. We deal with multiple populations and we run differences, hypothesis tests on the differences of those. What we call that is the one-way ANOVA. And in our class, we are going to focus on one-way ANOVA this week. We will not do anything more than that, although in the future classes, you will learn also multiple ANOVA tests. That is called MANOVA. This is a little bit more complicated method, and it considers differences of the populations, ways of dropping variables with high collinearity, and things like that. So the one-way ANOVA test is important for you. One thing that I want to also let you know is that this week in our readings, except of the ANOVA, the one-way ANOVA test, we are going to cover correlation. But from your posts, and I checked first and second week posts in the discussion, I see that almost everybody in the class has a very good understanding of correlation. So I will not devote much time on going over correlation itself. Next week, we will talk and review correlation and talk a little bit more about linear regression. We will talk about linear regression and normality plots and how to perform those in R. This is next week, but at the same time, because these 2 weeks basically they are together, they are somehow combined into one. I will start this type of discussion in our practice problems. Actually,
Professor.
Yes.
So, this week in the practice problem, if we just concentrate on one-way ANOVA, is that sufficient, or should we put problems regarding regression as well in this case?
This is what I'm saying. The readings for this week cover both ANOVA and correlation, and the let's say the introduction to regression, the relation between correlation and regression. Everything is covered this week, although the more in-depth regression and how to do it in R will be covered next week. Okay, so I will share with you some examples on regression and how to do it in R in the practice problems starting this week. So you can focus on ANOVA in the practice problems. That's fine with me. But remember that this week also is a week that the test 4 is due, and in the test 4 you will find problems on correlation and introductory problems on regression. Okay, so make sure that you complete the readings as they appear in your syllabus for week 8.
Okay,
perfect. So going back to ANOVA, as I said, we call it one-way analysis of a variance, and it's nothing else than a hypothesis testing technique that focuses to compare the means of multiple populations in the same way that we did the test last week on comparing means of 2 populations. The hypothesis, depending on the claim that we have, will be again a pair of hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis will be always the same, considering that the means of the populations are equal, while the alternative hypothesis, again, will be the same for all tests, and it will be simple. What the alternative hypothesis says is that at least one of the means is not different from the others. Now, by looking at the hypotheses themselves and how we set them up, we can see one thing that I want to make sure that we understand. The claim will be either that all the means of all the populations that we consider are equal, or at least one of them is different. The test will never help you identify which one of the means, which one of the populations has a different mean than the others. So the test only identifies, the only thing that it does is it recognizes if there is a population with a different mean, but it doesn't identify which one of the populations is the one that has a different mean. This is something that you should do in a subsequent test, where you will identify yourself which one of those has a different mean. Now, of course, this can be done by comparing the means into pairs. The requirements that we have for the ANOVA test are that each sample that comes from each population must be randomly selected, the samples must be independent of each other, and every one of the population has the same variance. Each population must have the same variance with the others. This is a very important requirement, and we need to run a different test in order to verify that. The test statistic that we use for the fourth step of our test is just a ratio that gives us the variance between the samples and the variance within the samples. And these are two concepts that we will discuss and try to explain with a specific example that I have here for you, that we'll discuss it together. The variance between samples measures the difference that is related to the given sample. It's called also mean square between. It really, the way that we notate each one of the different variables here, each one of the different formulas here, is a little bit awkward. And we need to see, in my opinion, you need to see the actual example in order to understand the differences. So instead of going through this presentation, I will go immediately to the secondary presentation that I have prepared for you in order to go and dive into a specific problem and look at it step by step. We already saw that. This is the way that we set up from the claim the two different hypotheses. And what we want to do is to look at an example. A random sample of students in each row is taken. Where am I? Here is the explanation of the situation. We know, and this is actually a true situation, that there are some statistics, classroom statistics, that they show us that students that they sit on the front, middle, and back rows, they tend to get different type grades at the test and finally at their final grades. Now, when we talk about a class, an actual class, and face-to-face class, we have realized that most of the times students that they sit on the back row are the students that they get lower grades. Now, if we want to transfer these to an online environment, it is more apparent because it seems that the students that they get late into the discussions or they do not they send the fewer number of messages to the professor and to the class are the students that they get the lower grades. This doesn't mean that each one of them, of course, gets the lower grade. We have exceptions. But overall, it seems that the students that they sit on the last row, on the back row, are the ones that they do worse on the exams. So let's look at an example based on that. We take a random sample of students in each row. The score for those students on the second exam, on an exam, was recorded. The front row has the following grades. The middle row has different grades, and the back row has different grades. Now, one thing that I want you to pay attention is that each one of the rows has a different number of students. No one requires to get samples that they have the same size for each one of the rows. We are fine by getting samples of different size for each one of the sets that we are comparing, for each one of the populations that we are comparing. The only requirement that we have is that each sample has the same variance. Now, we look at the summary statistics for each one of the rows. The front row, the middle row, and the back row. We see that the sample sizes are different. The means, the standard deviation, and the variance. Now, you may observe here that the variance do not look equal at all. That's true, they don't look equal. But what we care about is not only the number that you get here, but the sample size that we have and the mean for each one of the rows in order to understand and run a test on variances and compare the variances and see if there is a significant difference between the different variances. Variation is the sum of squares of the deviations between a value and the mean of the value. Sum of squares is abbreviated by SS. Now, right here, we get this awkward notation that I talked about earlier today. We have the SSB, that is actually the sum of squares between, and SSW, that is the sum of squares within. And these are two values that we calculate in order to compare, in order to identify the differences of the samples. Sum of squares, we are calculating the sum of squares between, so we take the different population, the different samples, and we calculate the sum of squares between them, and the sum of squares within is for each one of the classes, each one of the different samples. Then we are going to also introduce another variable, that is the SS total, and this is the sum of squares and is the variation. The variation is what we talked about, is the sum of squares of the deviation between a value and the mean of the value. All these we will see exactly how we calculate them on the table that I will show you right here. One thing that you need to keep in mind is that there are two sources of variations. The variation between the two groups, then this is the SSB, and the variation within the groups. And this is the variation that cannot be explained by the factor that we will calculate in order to compare the variances. Now, this is called the error variation. So basically what we are doing now is that we are going through the notations, and we will discuss it again as we fill in the table with all the information. The table that you see on your screen is very similar to the table that you will see in black, while there is one column in black that is missing, and I don't remember which column is the one that is missing, tell you the truth at this point. But it's very similar to the one that you get from R. So here is how we calculate everything. The first thing that we want to see is the grand mean. The grand mean is the average of all the values when the factor is ignored. And it is nothing else than a weighted average of the individual sampling means. Weighted average of the individual sample means. So we take the means, the averages for each one of the samples, and we create a weighted average based on the sample size for each one of the samples. How do we do that? Using this formula. So remember that the samples that we have for our problem was 7, 8, and 9. And then we had a mean for each one of those samples that was given up here. So we had the mean, and we also had the sample size. So if I take 7 times 75.71 plus 9 times 67.11 times 8 times plus 8 times 53.50, I will get the numerator of this formula. And then I divide everything by the sum of the sample sizes. So all the points together. This is how I get the grand mean. The grand mean for the specific example is 65.08. How do I calculate the SSB now? The SSB, as we said, is the sum of squares between the two classes. How do we calculate that? Well, we take the sample mean, we subtract the grand mean, we take the square of that, and if you see it, it reminds you the regular variance formula. You multiply that by the sample size for each one of the samples, and then you sum all of those. So if you look at the formula right here, basically you will have 7 times the mean of the first group minus the 65.08, that is the grand mean, squared, plus 8 times the sample size mean for the second group, for the middle group, minus the 65.08 squared, and so on. And this is how you calculate the group variation, the SSB. If you want to do this calculation, the result will be 1902. Now the group variation. How do we calculate the group variation? The sum of squares within a group. Well, in this case, we take the degrees of freedom for each one of the, degrees of freedom for each one of the samples that we consider, we multiply that by the standard deviation squared for that sample, and we sum them up. This is what we do. The degrees of freedom for each one of the samples is nothing else than the independent variables considering the specific sample, and since we are talking about one sample, it will be nothing else than the sample size minus 1. So for the SSW for this problem will be 6. Remember, the sample size was 7 times the sigma squared, right? The standard deviation squared. And I don't remember which slide was that. And your calculation will give you 3386. Now, let's go in here. This is where you get your SS, the sum of squares, for each one of the cases, between, within, and the total. And you plug in your values. You have the between, and you have your within. You can just add them in order to show the total. Now, one thing that you need to understand is that this basically shows you the variance that is explained of the difference from the difference of the differences of the two populations. Let me rephrase, of the populations taking them by two for the test. The within is the sum of squares that it comes from inside a sample. This is what we call basically the variation that is not explained by the difference of the populations. This is the not explained variation, while this is the explained variation, the one that it makes sense, the one that comes because of the difference of the populations. The sum of them will give you the total, 5288. Now, this is the degrees of freedom. And the degrees of freedom, they are a little bit strange, as you can see. How do we calculate the degrees of freedom? Well, it depends for each one of them for what row you are calculating. So for the first row, if you look at that, you have three different populations. So you are looking for the degrees of freedom for the independent variables based on the samples that you have. You have three samples, the degrees of freedom will be 2, 3 minus 1. Now, how do we calculate the within? The within group is going to be the sample sizes of the different samples for each one of the populations. So you will take the degrees of freedom for each one of the samples. The first one, the sample size was 7, 9, and 8. You subtract 1 for each one of those. So overall, you subtract the number of the populations that you started with. And you end up with 21. If you add up all the sample sizes, the answer will be 24. 24 minus 3, the number of the populations or samples, will give you 21. And this will be the degrees of freedom for the within. The total will be 23. That is 21 plus 2. Okay, now we want to complete now the third column. The third column corresponds to the mean of squares that is called MS. Again, for this one, we have two different means of squares. One means of square for the between and one means of squares for the within. They are nothing else than the average square deviation from the mean, and the way that we find it is we divide the SS by the degrees of freedom. This is how we find the variance. The variation divided by the degrees of freedom. This is how we find the means of the squares, the variance. So the MSB will be the SSB divided by the degrees of freedom for between. The MSW, it will be the SSW divided by the DFW. And the MS total will be the SS total divided by the DF total. Now, one thing that you need to pay attention is how you calculate the MS total. For all the other columns, we add the numbers to get the total. For this right here, we don't add the numbers. We do exactly the same process. If you add the numbers that you get on this and on that, cells, then you will not get the right MS total. How do we do it? We calculate them and we divide by the degrees of freedom. The result is going to be 951, 161, and 229.9. As you can see, 229.9 is not the sum of them. Of course, the reason for this, the reason that adding them up doesn't work, it has to do with the PEMDAS. I'm pretty sure that you remember that, the priority of the operations. And since we have a sum of numbers at the denominator, this doesn't work. We cannot just add the numbers. So
that's basic mathematics.
Right. It's simple mathematics. It has to do with the ratios that we are working with for the variance on this column. Okay, and now we are ready to look at the, here, at the Ftest. What is the Ftest? The Ftest is the number that we are looking right here, the number that we will put on this column right here. And this number, the Ftest, is nothing else than the ratio of the two sampling variances. So we calculate the two sample variances. We already have them, the MSB and the MSW. We divide the two of them in order to find the Ftest statistic. And the Ftest statistic for this case is 5.1, is nothing else than 951 divided by 161. What is the 5.1? I'll come to that in a moment. The Ftest statistics, the Ftest is a right tail test. So we have an actual test that we run for the Ftest. It is a right tail test and it corresponds to the F distribution. The F distribution is a right-tailed skewed, the right skewed distribution, and has and corresponds the numbers on the table. If you look at the F table, it will correspond to the numerator of the F test and to the denominator of the S test. When we run the test, the way that we run it is exactly the same as we have done before. So we are comparing the p-value of the area to the right of the test statistic. If the F test statistic that we find is greater than the than the critical value that the F table will give us, then we are going to reject. Otherwise, we will not reject. For the specific problem, we calculate the F, and this is 5.9. Now, if you run the F dot test in R programming, it will give you the p-value, and the p-value will be 0.009 in this case. The p-value, you compare it with the confidence, with the significance level. This is assume that at the beginning, when we start the problem, we assume that significance level of 0.08. So the test is exactly the same. We consider the p-value that corresponds to the critical value 5.9 of the F distribution. We consider the p-value and we compare that with the 0.05. Since this is smaller than 0.05, this means that the 0.09 is an area smaller than that on the right tail. And since this happens, of course, this means that the critical value, 5.9, falls in the rejection area. So what happens then? We reject the null hypothesis. So the way that we run the test is exactly the same as we have run every other test before that. What does this mean, then, for our problem? That there is enough evidence to support the claim that there is a difference in the mean scores of the front, middle, and back rows in the class. Why? Okay, let's go back. What did we do? We reject the null hypothesis. What was the null hypothesis? That all the populations, front, middle, and back rows, have the same mean. They don't have any significant difference between their average averages on the score of the student. But we reject that. So what does this mean? This means that we have enough evidence to believe that there is one of those populations, either the back, the front, or the middle row, that they have a significant difference on the average of the test scores. As I said before, one thing that you really need to remember is the ANOVA doesn't tell which row is different. You would need to look at the confidence intervals in order to do that. Any questions on that? Does it make sense, the steps that you are taking?